All right, hi everyone. Yeah, so we're back with another little stream here. And yeah, we'll be kind of following up on what we were talking about last week. I know I said it would be maybe another week or two before I got back to this, but I was a little impatient and I wanted to try to finish it up. So that's why we're back here so quickly. So the just to recap, what we're working on here is a virtual analog model of this guitar pedal circuit. This is the Crowther Hotcake. There's a few different versions, but I guess this one's from 2008. Yeah, we'll just be taking a look at this circuit and trying to finish up our emulation of it. And so where we left off last time, we had come up with a net list for most of the circuit. So this is a little bit of a complex topology. And so we decided that we needed what's called an R-type adapter to model this topology. And we set up a net list for that R-type adapter. And then we had been trying to generate a scattering matrix for the adapter. And that was kind of where we got stuck at the end of our time last week. So now we're just picking up on it, and I've spent maybe, I don't know, 20 or 30 minutes in my free time here working on getting some of the work sort of brought a little further for this time. And I'm happy to report that I was able to generate a scattering matrix. So turns out that when I'm not running Zoom on my computer, Mathematica is able to work a lot faster. And so it ended up taking maybe, I don't know, 10 to 20 minutes to generate the inverse of this complicated matrix and then generate the full scattering matrix here. And yeah, this is kind of a beefy matrix, as you can see. But fortunately, we can just kind of trust that Mathematica did the right thing and not worry about it too much. Which is nice. So yeah, the C++ compiler will kind of boil this all down to something more manageable. And the other thing that's nice, which I can show you guys in a second, is that we don't actually have to run this at every sample that we're trying to process through our circuit model. We only need to run it when the controls are changed, when the parameters are changed. And by run this, what I mean is that we're sort of evaluating all of the terms of this matrix. We only need to evaluate those terms when we're changing the parameter values. So yeah, we've got our scattering matrix, and from there, we've got this WDF model that I've started putting together. So first thing we have here is our port A, and this is basically everything in the circuit up to the positive terminal of the op amp. So we've got our input voltage, we've got our capacitor C1 here, we've got our bias voltage and the resistor in between, and then we've got this R2 resistor that goes into the positive terminal there. And so we're working that out here in the WDF architecture with our input voltage source here, capacitor C1, our bias voltage with the resistor attached, and then our resistor R2. And let me make everything a bit bigger once again so that it's easier to see. So hopefully that's visible for everyone. So that's our port A going into the R-type adapter. Next, we've got our port B, which is this kind of ground, this path from the negative terminal here to ground, so through C2, and then through these other two resistors, which we're going to just combine into one resistor in the WDF architecture, which we'll call R4, R drive. That's basically what we've got down here at the bottom. Then we've got port C, D, E, and F, which are just these one element things. So one is this R3 resistor here. We've got another for R5. We've got another for R6 and for C6 going to ground. And then we've got our presence potentiometer, which has both the positive part, which is this top part here, and the negative part, which is this bottom part down there. And then finally, we're almost done here. We've got port J, which is C7 and R7. So that's this little path to ground from down here. And then finally, we've got port K, which is kind of where the output of our circuit comes from. And so that's going through these two capacitors here, which we can combine into one, and then going through the level resistor down there. So that's our circuit model in short. And then basically what we want to do from there is create an R-type adapter, and we're going to call this a root R-type adapter, since this is going to be at the root of our circuit. And there's a few reasons why we want that to be the case, which I can explain in a bit more detail. But basically, we're going to connect all of these ports to our R-type adapter. And then the scattering matrix is being set here. So basically, we're taking our port impedances, which are all of these same variables that we were using to generate our scattering matrix here. So if you look at the matrix that we're working with over here, it'll be all the same variables that we're dealing with in the code here. And then I've got this matrix setter function, which I might regret this, but I'll try to show you all here. This is basically just a copy paste of the Mathematica, of the scattering matrix that Mathematica gave us. So that's all just being set in the function here. The reason why I put it, in its own file is because it's such a massive scattering matrix that C-Line kind of has trouble keeping up with all of the stuff in this file. So by putting it in its own file, it doesn't make C-Line slow down too far. So this R-type adapter here is where all of the scattering matrix stuff and all of the op-amp model stuff is going to happen. And basically the idea for this is it's kind of what we call a functor, I think, in C++ terminology. And the idea is that this is how we update the impedance of the ports that are facing the R-type adapter. And again, I can go into a bit more depth on that if folks are interested. But then when we actually go to use the model, it's pretty easy. So our capacitors just need to be prepared with the sample rate. And then our bias voltage is just set to some constant voltage, which I'd gotten from a SPICE simulation is 4.9 volts. Well, it depends a little bit on some of the other settings in the circuit, but for now we'll call it 4.9. Then we've got our parameter setting here. So for our drive is going to be set depending on where our drive parameter is. And then the presence potentiometers are going to be set depending on where the presence parameter is. And actually, I messed that up a little bit. That should be RP and RM. Ooh, that's a little embarrassing. And so I may need to actually flip these. I'm not sure which side needs the 1 minus parameter for the resistor there. And then, as I mentioned to myself in a comment here, I might need to skew the drive parameter some just so that it seems like it's in the right range of values. Yeah, so that's basically our circuit model. And then when we go to process a sample of audio, we can just set the voltage of the input voltage, compute the R-type adapter, and then extract the voltage of the output potentiometer, the output resistor, and that will basically be our full circuit model there. So yeah, let's build it, and then let's do some measurements in Bitwig and see what we get. So yeah, a lot of stuff here. Hopefully it wasn't too overwhelming. Yeah, please ask some questions or slow me down if there's things that you want a bit more elaboration on, or if there's things that you missed from last time we were talking that you might want a more in-depth recap of. I'm going to go ahead and close Wolfram because I don't think we really need it anymore. But yeah, anyway, so this is just a little testing session that I've made here. So I've got a limiter just in case something goes wrong. I don't want to blow out my eardrums or my speakers if I was using speakers. And then I've got the plugin in here. And for now, I'm just going to wrap the plugin with this EQ curve analyzer so we can see the frequency response that we're getting. Cool, yeah, so this is kind of interesting. Maybe I'll put that over there. So let's make this nice and big. Yeah, so we can see the frequency response, and we can see that maybe the level goes down when we move our drive parameter, which is kind of what we expect. Yeah, so we can make the level go down pretty far, or we can bring it up really high. So yeah, I think this is where I'm going to need some skewing of this parameter, because right now, as you can see, when you get close to 100, it gets really high, really fast right there. Yeah, so maybe we'll try to figure out the right sort of skew for that parameter, and then let's see what's happening with our presence. Yeah, so I think I have this flipped, since usually presence means you've got like a bit more of that mid-range. So yeah, I think I need to flip this control, but that's kind of interesting what it does to the frequency response there. So that's pretty neat. All right. So what do we have left to do here? So we've got to fix these controls a little bit, which shouldn't be too hard. And then we've got to make this make this circuit actually distort a little bit, since right now it's not distorting at all. It's just a completely linear process. And we can prove that to ourselves actually if we put a sine tone through the plugin here. So there we go. And if we look at the frequency spectrum, we can see that no matter what we do, we're just getting one sine wave back out. Whereas if we had some distortion, maybe we'd be getting some more harmonics. Actually, we probably will see a few harmonics just because I've got the limiter here and we're hitting the limiter a little bit. So we're getting some distortion from the limiter. But if I turn the limiter off, then yeah, nothing really important happening as far as distortion. So these are some things that we want to improve. So let's start by looking at the controls. I think that'll be useful. Oh, and actually, I can show you guys this as well. I put together a little spice model of the circuit, just so that I can get a sense of what the output should look like. So here, bring back the screen share. Get rid of all my other tabs. Okay. Yeah, so I did this on my other computer because I don't have Spice on my Mac computer. But this is basically the op-amp clipping that we get when the transistor is being bypassed. So depending on which mode you have the pedal in, this transistor may or may not be operational, might be bypassed. So this is the bypassed version. And so you can see we're getting some op-amp clipping, which is kind of an interesting shape. So yeah, let's see if we can recreate that. And yeah, I've put together a few things that will help us get there, but yeah, we'll see what happens here. So first, I'm just going to flip the minus and plus parts of the presence potentiometer, so that way that control will be effectively flipped. And then for the drive parameter, I'm going to add some skew. So maybe the problem was that sort of between 0.9 and 1, we were getting a ton of range in the change of the gain. So maybe we want to limit that a little bit. And so I think I'm going to skew it with a number less than 1, which should kind of give it more of a arch shape instead of like a parabola shape. And that should help to kind of smooth that out a little bit. I'm also going to do this thing that I've done elsewhere, but I don't remember how to do. I always forget this trick. But the idea is that we're going to want to not update the R-type adapter until we've finished updating these other things here. So maybe I'm not doing it here. Yeah, I guess I'm not doing it there. I'm going to search for it. Impedance change. How do I spell this? I saw it just a second ago here. Yeah, here we go. Okay, this is what I want. So this will defer all impedance changes for the components that I use it on until it goes out of scope. So what we're going to want to do is defer impedance changes to the R-type adapter until we're finished setting these other resistor values. And basically what that's going to do is that's going to put off calculating this scattering matrix so that we only have to do it once whenever we set these parameters, whereas right now we would be doing it 3 times, once when we set each of these resistance values. And that's a bit wasteful, so we don't really want to do that. So yeah, I think this would be good for our parameters, but let's take a look at it here. Yeah, I wonder what that giant scattering matrix is doing to our compile times here. That might be slowing us down a little bit. Okay. Let's take a look at what we've got. Yeah, so that looks reasonable. So yeah, now maybe, well, I'm not seeing a whole lot of difference in the behavior of this parameter. Maybe we need a heavier skew, or maybe it's okay. Well, we'll know a little bit more once we get a bit of testing with the distortion going on. Okay, yeah, so that's looking pretty decent there. Cool. So now let's try to get some distortion happening. So what I've done here is I've made a copy of the root R-type adapter, which I'm going to call the flapjack op-amp R-type, because we can put our op-amp clipping into this R-type adapter. And that's what I've got over here. So basically, what I'm doing here is after I run everything through the scattering matrix of the adapter, I'm going to have some nonlinear function here that's going to do something to clip the signal in some way. And so right now I'm just using a hard clip. And yeah, right now it's just doing everything on scalars, but I think we can make that a little bit better here. So let's do this. So we'll use SIMD to basically run everything through this nonlinear function for values at a time instead of one value at a time. And yeah, so let's do this. So we'll do const auto a val. Yeah, we'll do a batch. How about equals SIMD road aligned a vec plus I. And then same thing with b batch, except that'll be with b vec. And now we can figure out our voltage, which will just be the same thing that we have, except with the batches instead of the scalars. And then, yeah, this will also be a batch. And then we'll do an XMD store aligned here. So store aligned, this will also be VVec plus I, and then it'll be that value that we're putting in there. Cool. So the real magic, the real important thing is happening here, where we're clipping the voltage between 0 and 9. So this is basically a hard clipper. And the reason why I picked 0 and 9 is because those are the voltage rails of our op amp. So the negative rail here is ground, which is 0 volts. And the positive rail up here is plus 9 volts, which is, I mean, okay, VA might be slightly less than that, but for now we'll just say 9 and we can tweak it later if we want to. And again, this should give us a clipping shape that looks something like this. You might say, oh, that doesn't look a whole lot like hard clipping, and that's just because there's some other filtering going on in the circuit. So we've got this sort of DC blocker at the end. We've got this capacitor going to ground here, which is adding some filtering. We've got, yeah, all of the capacitors basically add some filtering to the signal that makes it look a little different than your usual hard clip. But anyway, this should give us something that looks reasonably interesting. So let's take a look. Oh, someone's not happy. Okay. I need to refix these with the data functions so that I'm actually pointing at the data that I want to point at. And then I don't want to use STD clamp here because I want to use XMD clamp instead. Does XMD have a clamp? Oh, yes, it doesn't. Maybe it's called clip. Yeah, there we go. All right. That's a little bit more audio style anyway, so that's kind of nice. Let me just read the documentation here to make sure it does what I want it to do. Okay, yeah, low and high. Clipping, perfect. Oh, okay, I gave it the wrong arguments. Let's just give it a template, and I think that'll make it happy. Oh, still not happy. All right, what do we got here? Candidate template requirement is scalar. Was not satisfied. Oh, interesting. Huh. Maybe I'll do this instead. I think this will make it happy. I feel like XMD has gotten a little bit more strict about some of the stuff recently, which is probably a good thing since it probably helps avoid some like undefined behavior and other funky things that you can catch yourself with in C++. Yeah, so basically clip wants to have the same type of argument for all three arguments. And before I was giving it a XMD batch and then a float and another float. And so now I'm giving it 3 XMD batches, and that should help. Cool. Yeah, so that'll compile. Nice. Cool. So now we'll use this test tone. And let's take a look here. So yeah, the frequency spectrum looks better. Now we're seeing some harmonics. And on the oscilloscope, yeah, that looks good too. So yeah, we're seeing some actual clipping now. Maybe it's a little bit harder, a little bit of a harder clip than what we were seeing in the spice diagram, but maybe that's okay. Yeah, that's an interesting looking clip. I'm gonna listen to it here for a second. And then I'm probably going to want to adjust some of these parameters. That's kind of interesting. So we get a little bit different shape depending on where the presence parameter is at. That's kind of neat. Yeah, it's interesting. You kind of get a sharper points at 0 and 100 and something much rounder in the middle. That's kind of interesting. Maybe not exactly what I would have expected. But anyway, I'll just put this at 100 for now. So yeah, maybe around 50, we've just gone back to a pure sine wave. So yeah, maybe we want to start skewing this parameter even more. So yeah, right there around 75 is where I'm starting to hear some distortion. Yeah, and then that last bit of ramping up at the end is still fairly aggressive. So maybe we can skew this parameter a bit more here. But overall, I'm very happy with that. I think it's sounding pretty good. Yeah, I think that'll be a cool sound. I'll try it out on my guitar in a minute here, and maybe I'll try to pipe the audio through to you as well. Yeah, but now we get into the actual fun stuff, which is that we've got this basically this place where we can put a nonlinearity in the circuit model. And I think there's probably some limits on what we can do with that nonlinearity, but we can kind of experiment and have fun and see what might sound cool, even if it's not necessarily exactly what's in the original circuit. And so that's going to be a fun time. So I'm pretty excited to start playing around with that here. All right, so yeah, we've got drive at 0, and now as we bump it up, oh, weird, that seems more more of an extreme change than what we were seeing before. Maybe I'm skewing it the wrong way. That's totally possible. Yeah, maybe I'll try like 5 or something. So this is like 1 over the numbers I was trying before, basically. But yeah, so I'm thinking right now we've got this kind of hard clip going on between 0 and 9. I'm thinking maybe we'll want some kind of tanh like soft clip, and I think that'll be fairly close to what we're getting from the original circuit when the transistor is active. And then we'll also want to play around with I don't know, maybe some other strange shapes that might give us interesting results. We'll take a look at that in a minute here. So as we crank up the drive, yeah, that's much better. Although we are getting a little bit of graininess when we change that. So probably I want to add some parameter smoothing for that. So I'll make a note to myself there. Let's parameter smoothing. Cool. So that's decent. I'll just make that a little bit more normal. Yeah, now we can have fun. So let's open up a Desmos thing here. How do I hide this? How do I hide this thing up here? There we go. Yeah, so let's make some clipping functions. This will be fun. So let's see, we've got y equals, basically we want min of 9 and the max of 0 of x. So this is our hard clip that we've got now. Pretty simple and straightforward. Maybe the next kind of basic thing we would want would be like a tan H. I don't love using tan H's because they're kind of expensive, but let's just see what that would look like. So we would want center to be maybe at 4.5 here. And then maybe we would want to multiply this by 4.5 as well. And then probably plus 4.5 puts us there. Yeah, that's maybe a bit, I don't know, a little bit too steep here in the middle. So we want to make sure that the slope of our nonlinearity never goes above 1. And the reason for that is that I think it will make our circuit model go unstable here. Just because this is all happening within this wave digital filter where things are being passed around recursively. So yeah, we want to keep the slopes fairly low. Let's see. Yeah, that looks a little better. Oh, hey, George is here. George says, hello, I got the notebook working in Jupyter, but matrices displays 2 elements per line. Yeah, working with large matrices in Jupyter can be difficult, as you've noticed. But yeah, anyway, I was able to get the scattering matrix working. So if you just want that matrix, I can send it to you, or actually it should be on GitHub already if you're looking for that. So that's our tan H function. I think I like this other function a bit better though, which I'll show you guys here. So this is, I first saw it in one of David Ye's papers, but I heard someone a little while ago call it the algebraic sigmoid, and I like that name quite a lot. That's a good name. But basically what we're going to do is this. So we get kind of this tan H-like response. And so now we just want to do the same scaling that we were doing up here. So let's do this. That gets us close-ish. Yeah, that's pretty reasonable. It's maybe a little bit shallower than I would like, but I guess everything's going to be shallower than your hard clip, won't it? Unless you make the slope larger than 1, so that's okay. Yeah, the other thing that you can do is just add a term here. So you can just put like, I don't know, a 2 there. And now it changes kind of where the clip ceiling is. So numbers larger than 1 make the clip ceiling a little bit tighter. and numbers smaller than 1 make the clip ceiling looser. So that's interesting. I wonder if it's okay for these numbers to go below 0. I bet it is. Maybe we'll try something a little bit closer to the tan H like that. That's pretty neat. Let's see, maybe if we want to get even closer to the tan H. So that's 0.8, 0.9. That's kind of cool. Maybe I'll stick with 0.75 for now. But yeah, so now we need a way to switch between the different clipping functions here. So let's add a couple of controls. So basically, these controls are going to be the corollary of the mode switch in the pedal. And then I also need a switch for the XLF mode here, which, as I understand it, stands for extra low frequencies. Since I guess probably the, let's see, probably the 47, yeah, the 47 nanofarad capacitor will let more of the low frequencies through. So that's our XLF mode. But yeah, we'll test that out. So let's add some parameters here. So we're gonna want a bool parameter. Then we're gonna want a choice parameter. Mode parameters. Yeah, and so now we get to have some fun and experiment with some different nonlinearities that might give us a cool response. So let's see. In place parameter, we'll make a bool parameter here, and this will be XLF. I don't know, I might want to give that a better name. That's okay. And then for the choice parameter, we'll call that mode. So let's see. I don't remember the names for the original different modes in the plugin or in the pedal. So we'll call this op amp clip. We'll have one which we'll call transistor clip. I feel like these names are going to be too long though. But whatever, we'll just see what they look like in the UI. There we go. And then we can load our parameters here. So we've got our mode param coming from there, and then we've got our XLF param coming from there. So let's see. This is going to be a discrete parameter, so I don't want to group it in with these guys, maybe. Well, maybe it's not that big a deal. I'll just toss it in here. Cool. Excellent. On. And then we'll do, this is C8, C9. Set capacitance. So if XLF is on, this will be 49. Is that right? 47. And then that's nanofarads, right? Not microfarads. Yeah. Nanofarads, and otherwise it's going to be 147. Oh, the F's and the places aren't There we go. That's silly. Anyway, yeah, so we've got our capacitance values coming out here. Yeah, so that makes sense. And now we want some way of having our different clipping functions represented. So I think I'm going to use an enum for this. So let's do this. We'll have an enum class here, which we'll call flapjack clip mode. Right. And well, yeah, I'll think about this a little bit more here, but basically, yeah, basically this should be hard clip, and then we'll do algebraic sigmoid as the next one, and then maybe we'll add some others later on. And then I'm going to make this a template argument here. So, well, yeah, this will be fine. Don't worry about it. Template, flapjack clip mode. This will be the clip mode thing here. And so now is where we're going to want a bit of space to implement these functions. So if clip mode equals flapjack clip mode hard clip, then we'll just do this function that we've got here. Oh, and this can be an if context word, which will help the compiler optimize it. Flapjack clip mode algebraic sigmoid. Here we've got to do a little bit of fanciness to get this going. So we're going to have a inverse square root here, and so there's a way that we can get that going. So let's see. Const auto denominator equals x and d r square root. So this is the reciprocal square root function. This is going to be 1 plus 0.75 times that. 0.75. I've got the plus here. Times, what's this? X over 4.5 minus 1 squared. So we can square it. This is x over 4.5f plus 1. Oh, not called x here, is it? It's voltage. And then we also don't want to use a divide here. So let's pre-compute that. There's probably some easier form for that, isn't there? Not really. That's okay. Times r 4 and 5. And that should be our denominator, right? So we've got 1 plus 0.75 times the square of x over 4.5 plus 1. No, minus 1. Good to catch that. And now the voltage is going to equal voltage minus 4.5 divided by denominator. Oh, whoops, times denominator, because we did reciprocal square root. That's a little bit of a misnomer there, maybe. And then plus 4.5. So I'll call this our denominator, just so we know it's the reciprocal. Cool, that should be correct. And now we've kind of got to propagate all of this stuff back up to where we're calling these functions. So we've got to add a template here. Flapjack clip mode. Cool. And then here's where things are going to get a little bit more wonky. So let's see here. We want the enum value for Flapjack clip mode of the choice param, which is the mode param. Get index. Yeah. So let's see. Clip mode equals that. There we go. And now we can do there's a function for this. I just used it the other day. Is it visit? It is not visit. Let me find out what it is. No, these are tuple helpers. That's not what I want. Let's see if I can find it in the documentation here. Oh, I bet it's enum switch. Yeah, that's the one. All right. This is what we're going to want here. So first, let's make sure that we've got the right type. Well, we'll find out in a sec. Enum switch. Cool. And then we can just put this in the buffer in our capture list. And now move all of this stuff into the lambda there. Oh, and the channel index, although it probably won't let me do that directly, will it? Yeah, for some reason, I don't fully understand this, but C++ doesn't like it when you pull or when you capture something from a structured binding. I don't know why it kind of flips out over that. Anyway, there's a better way to do this, which is just to bring the for loop inside as well. Maybe that would simplify things a little. Or maybe not. This kind of thing never really looks great, no matter how you do it. Let's see. So now we can template on the mode here. Maybe. Cannot assign to a const qualified type. Oh, that's because this should be a reference to the buffer. There we go. That looks a little bit nicer. So now we should be able to set the set all of the clip modes from this enum parameter kind of thing. And I'm setting the XLF mode there as well. I'm going to switch the drive and the presence params to be smooth buffer values. And this will allow me to smooth them as well. Yeah, and then, well, I may have to do some other things in there to get these to be a little bit more. I may need to change the way that we're doing the drive parameter here so that it works out okay with the skewing that we're doing later on. Well, no, I think that'll be okay. Yeah, I've got an idea how we can do this. So let's see here. So drive param dot set parameter handle. And we'll just use this guy here with get parameter pointer instead. And then we need to give it the parameter type. Cool. And then we can do the same thing with the presence param. And then let's see, drive param dot set ramp length. I don't know, 0.05, maybe a little smaller is okay. We'll do the same thing with the presence param here. So presence, I think, is fine as is. I don't think that needs any modification. With the drive parameter, I would like to set the mapping function to take care of our skewing for us so that we don't need to do it every sample. So let's see what we're doing here exactly. So here we're doing 1 minus x. So let's do that here. And then here we're doing a square. Okay, that's not too slow. Well, let's just do it here anyway, just to make things easier. All right, and now we need to prepare those as well. So let's see, drive param, prepare. And so here, what we're going to want to do is we're going to want to process the parameter smoothers. Yeah, and then here, we're going to want to check if we're smoothing or not. So we'll say if drive param is smoothing or presence param is smoothing, then we'll want to do one thing, else we'll want to do something else. So when we're not smoothing, we can basically just do what we're already doing. And so that's just drive param dot get current value, and same thing there. when we are smoothing, we'll want to basically move this inside the loop so that we update the smoother, we update the parameters every sample. So let's see here, const auto star drive smooth equals drive param dot get smooth buffer. Okay, George has a question. We'll get to that just in a second here after I'm finished with working out this parameter smoothing. Okay, and then also I'll get the XLF parameter out of there so we don't have to query an atomic every single time. Oh, and then we no longer need this 1 minus or the parameter skewing, because that's all happening in the smoother for us, which is kind of nice, because that only needs to happen once per block, even when we're smoothing every sample. So we'll do drive smooth. Okay. I need to get the index as well so that I can call all these other things too. So drive smooth and presence smooth. Cool, so that should take care of the smoothing for us. All right, so George is asking, are you clamping after the scattering matrix is calculated? Yes, so the reason why I'm doing that, and I'm not 100% sure about this logic, I might have something flipped around in my head, but kind of my idea here was that I would compute the scattering matrix. So I've got the incident waves in A, I compute the scattering matrix to get the reflected waves in this B vector. And then basically I want to modify the reflected waves to account for the clamping. I can't really modify, or I mean, I could modify the incident waves, but that wouldn't do anything because I'm just going to overwrite them again anyway when the next reflected waves come back in from the external ports. So basically, I'm just computing the voltage from the incident and reflected waves after the scattering matrix, since I believe that's when they're all sort of at the same time step, if that makes sense. Whereas if I were to do it before, I think B would be one time step prior, or the values in the B vector would still be the reflected waves from one time step previously. I mean, probably the more accurate way would be to do some kind of Newton-Raphson iteration, but it would have to be a global iteration over the entire WDF model. I didn't really feel like doing that here for a couple of reasons. But part of it is that this way allows us to kind of experiment with these funky clipping functions and just kind of have some fun with, hopefully making some cool shapes happen. But yeah, so I've got my parameters smoothing. So I think I should be good to go as far as giving this a try here. Hopefully I didn't make any new compiler errors. But yeah, if this is going well, maybe I'll add a third mode and then maybe just play some guitar and have some fun with it. Here, let's try here. All right, so we've got our we've got our little thing here. Okay, so I definitely want to move the XLF parameter into the menu up here. I forgot to do that. But let's see what we get. So that's the hard clipping mode, I would guess, since that looks the same as what we had before, roughly. I'll unmute so I can hear it a little. Yeah, the parameter smoothing is definitely helping. And then let's see what XLF changes. Maybe I have it flipped around. Maybe I need the other capacitor value. Yeah, it probably doesn't do much until we go to really low frequencies though. Yeah, it's a small difference, but it is noticeable. And then yeah, it's kind of interesting. And then let's see what changes with our different clipping modes. Now that's cool. All right. Yeah. So now we've got this kind of soft clip coming from our op amp. That's a little different from the hard clip that we were seeing before. I'm a fan of that. All right. Cool. So let's move let's move the parameter to the pop-up menu. So yeah, that's how I was doing it. So and pop-up menu parameter to be the XLF parameter. I should probably clean up these magic strings. Let me just do that real quick. So that's auto. Presence tag. Level tag. Mode tag. And XLF tag. Yeah, kind of not always in the best habits of using hard-coded strings versus putting them in constant variables, but you know, it is what it is. So yeah, let's think about what we want our next clipping function to be. And also maybe if we want to give them some different names. I'm not 100% sure if I want to do that or not. It might be fine to just leave them as they are. Maybe I'll look around online and try to get some inspiration from existing names that some of the different variants of the pedal have. That can be kind of fun. Cool. So that's taken care of. Here's the fellow whose article I was reading before. So, okay, so they've got the Bluesberry variant, which is what has the softer clipping. So, let's see. So we've got op amp clip, and then I'll call this one Bluesberry because it's kind of softer clipping, like you might get from the transistor. And then let's make one other clipping function here. So let's make this one be asymmetric because right now the hard clip and the soft clip are both kind of symmetric functions. So let's get something that's asymmetric maybe. So let's see here. see what just exp of x looks like. And maybe let's slow it down a bit. So the problem with using exp is that we need to make sure that the slope stays small enough. The slope stays small enough while we're in the range of what we're looking at here. So yeah, let me see. Maybe we should do like some kind of piecewise thing and see when the slope is going to equal 1. That could be interesting. So maybe we want to set it so that the slope equals 1 when we're at that point there, when we're at 9. Oh, George is saying, also, did you consider my suggestion to change the C8, C9 capacitance dynamically while keeping its state? Yeah, so that's exactly what's going on here, is we've got this capacitor here that's just changing its state, or sorry, changing its capacitor value depending on the value of the parameter. And thanks for reminding me, I also needed to flip those values there. So yeah, let's see if we can get the slope to be 1 right at 9, right? So basically we want e to the ax, right? So we've got this a parameter here. We've got e to the ax, and we want something down in the realm here, right? And we want the slope to equal 1, maybe at 9, right? So e to the x equals 1 means that what is it, log of x, sorry, log of 1 equals x, right? So let's open up Wolfram Alpha. So exp a times 9 equals 1. Right. So what is a? A is something imaginary, I guess. Yeah, I guess that makes sense, right? So then that means that we would need some offset term as well, right? So let's do ax plus b, right? And so that gives us a bit more leeway as well. That's kind of cool. Maybe we can just put this at 1 and just slide this around. Well, let's do minus b. That'll be a little more intuitive. So, I mean, we could do something like that, right? And so we want 9 exponent of ax minus b to equal 1, right? And maybe we get rid of that and don't care about it anymore. So let's try that. So 9 times exp of 9 minus b equals 1. And so b equals 9 plus log 9, which is this number, 11.197. Something like that. Okay, that's a little, yeah, it's maybe a little too shallow through most of this area. That's a little disappointing, right? Yeah, so slope is 1, maybe right around there, right? Yeah, I guess that makes sense, right? Okay, so let's see. There's definitely a way to kind of get this get this to work for us, right? Maybe we could do a log function even, right? So we got log of x plus 1 or something. Well, we want to make sure that we can do this in a way that's piecewise and kind of makes sense still, right? So we want to make sure that we've got that 0, 0 point, and then maybe we can go down after that. So maybe let's do this. Log of x minus 1. Oh, whoops, plus 1. Right? And so we can kind of do this piecewise. So below 0, it'll just kind of flatten out into that. Or maybe we can even do it like some kind of leaky sigmoid down there. That would be kind of fun. So that's cool on the negative side, but on the positive side, I want something larger than that. So maybe something like that. Maybe that's a little too much. Maybe somewhere in there, right? 8. Yeah, that's kind of fun. We can tweak it around a bit and maybe find the ideal setting that sounds the best. Yeah, and then let's see what we want to do on the opposite side, right? Because the slope of this is going to be, actually, we might be into a little bit of trouble here with slope, but we can deal with that if it causes instabilities when it comes. But down here, we've got log of 1, right? So our derivative is going to be 1 over 1, which is 1, so our derivative is 8. And so here we want some kind of exponential function that's going to kind of peel off for us there, right? So let's do y equals 8 times the xp of minus x, just b of x, right? And let's make sure that these are piecewise, right? So we want to do this where x is greater than or equal to 0. Right? And then this is where x is less than 0. Cool. So if I don't do that, then I've got this, right? So I just want to subtract 1. And that'll make those link up. And then I can multiply it all by 8. And that'll make the slopes line up, right? Sort of. It doesn't look quite right, does it? Let's see. Yeah, that's not looking quite right. So let's see if we get rid of those, right? So slope equals 1 when we're at 0. Yeah, so we just want to drop that down, down 1 and then times 8, right? Yeah, I think that's about right. Okay. But yeah, I don't love how far down we're going here, you know? So maybe let's change something here. Yeah, it doesn't have a whole lot of effect, does it? Well, let's see. Maybe that'll be okay if we get slope right here, maybe. So we have to go the other way here. Let's see, so we can have a control for it. And we want the slope to match up like that, right? Yeah, so Let's see, we've got exponent of cx minus 1. So let's see, dx of exp cx minus 1 equals 0 at x equals 0, does not equal 0, equals 8. Okay, maybe not. Interesting. Oh, that's because I put the minus 1 in the wrong spot, or at least partly because of that. Yeah, that doesn't seem quite right, does it? That looks pretty decent there, somewhere around 4. Yeah, any more than that, and it gets a little hairy, doesn't it? Oh, put a cap there. Yeah, somewhere around 3 or 4 seems to be the sweet spot there as far as getting those derivatives to match up. Yeah, why is the derivative behaving strangely, right? Because this is exp of cx minus 1. Exp of cx minus 1. So the derivative of that should just be c times e to the cx. So the derivative at 0 will just be c, right? So maybe that's 4. Seems about right. So let's see, what's the derivative of 8 times log x plus 1? Did I get that right? Yeah. Man, what would I do without Wolfram Alpha, right? So it's 8 over x plus 1. So when x is 0, that should be 8, right? Yeah, you would think. So then how come derivatives only look like they match when I set c equal to 4 and not when I set c equal to 8? Right? That's kind of an interesting anomaly. Yeah, something still feels a little bit off to me about this. I don't know what it is, right? So exp cx minus 1. Yeah, that's right. And then here I've got 8 log x plus 1, where log is the natural log, and that seems to be the case here as well, right? Let's double check that. Log base e. Okay, that is different. So it must have been using log base 10. That is good to know. I did not know Desmos did that. Okay. Let's get a smaller number than, here then maybe. So 4, that's still a bit too large, right? 2, 5, 3. Let's pull this guy back in as well. Okay, that seems reasonable. And then if I set c to that, then we should have our yeah, there we go. We've got our continuous derivative worked out nicely. Okay, cool. Yeah. So let's try that, see what it sounds like. All right. All this asymmetric. Skew equals 3.25, I guess. .25, cool. And so, yeah, we're going to want to do some kind of approximation here, which would be good. But basically, we're going to want to do voltage equals X in the select. So if we're doing X is, voltage is greater than or equal to 0, then it's going to be this log term here. So 3.25 skew times xmd log of x plus 1. Right, else we're going to want to do exp of cx minus 1. So SIMD exp skew times x minus 1. Yeah, now we can get rid of that old stuff. Cool, yeah, so we're probably going to want to replace the log and exp functions with some approximations, but we can figure that out later. For now, let's just add a choice to our choice parameter here, and we'll call it, I don't know. What's a good name here? So we've got op amp, we've got bluesberry. I don't know, bluesberry kind of has like a fruit theme to it. We'll call it peachy. I don't know. Maybe that's fun. Oh, forgot a semicolon here. Cool, yeah. So this has been a fun bit of exploration. I'll try to get this wrapped up here in another maybe 10 or so minutes. Okay, Revelo's asking, no antiderivative, anti-aliasing. That's kind of a tricky thing to do within wave digital filters is the problem. So the thing with antiderivative, anti-aliasing is that it adds some amount of latency to your signal. So for first order ADAA, you get half a sample. For second order, you get a full sample, and so on. And the problem is that inside of a wave digital filter structure, those delays will cause filtering and other kind of unwanted effects that will kind of mess up your circuit simulation if you just kind of do it in the normal way. There is a paper that I had seen, it was from DAFX a couple years ago, about doing antiderivative anti-aliasing inside of wave digital filters. It was a cool approach. It might be the best approach that's possible, but I didn't really love it. It seemed like a bit too kind of intrusive as far as keeping the rest of the wave digital filter structure intact. But yeah, like I said, there may not be any other way. So yeah, it's kind of a tricky thing there. So basically what we have here is that we're just relying on the plugins oversampling to take care of the aliasing artifacts for us. So in this plugin, we're always using 2x oversampling by default. And then, you can change that around if you want. But yeah, I guess if you are using this at 1x oversampling, then you'll definitely run into some unfortunate aliasing artifacts. So yeah, that's too bad. But yeah, I mean, I don't know. Maybe I'll think of some other aliasing helpers later on. Oh, interesting. Okay, so this is definitely creating some interesting shapes here. Yeah, it's maybe a little bit too quiet even. Maybe we want to make C a bit larger. Okay, so Revelo's asking, how does a wave digital filter work? Yeah, so that's kind of a big topic, but the basic idea is that we're taking our circuit and we're splitting it up into its component parts, and then we're basically thinking about it as if it was a sort of network of these individual components that are all connected through these things called adapters. And so if you have two circuit elements that are in series, we would use a series adapter to connect them. Or if they're in parallel, you'd use a parallel adapter. And there's different kind of ways of having the different circuit elements interact through these adapters. In this case, we have a kind of complicated circuit topology. So we have this thing called an R-type adapter. And that's what's giving us this array of what's called voltage waves to manipulate. But yeah, I definitely suggest, if you're interested in wave digital filters, I definitely suggest reading maybe the first, maybe half chapter or so of Kurt Warner's PhD dissertation. It's a pretty hefty work altogether, but the first 10 or 20 pages are very manageable. So that's probably a good modern introduction to wave digital filters. There's also a great paper by Alfred Fedweiss from, I want to say 1985 or something, if you're interested in sort of the historical aspects of it as well. Okay, yeah, so it definitely works, but it's there's a bit too much stuff happening all in the last range of the slider here. Whereas like with the other modes, you kind of get a smoother transition into your distortion. Yeah, so let's see if maybe we can work out a little bit nicer, something a little bit nicer for this version. Also, how much faster are the XMD log and EXP operations? So my understanding is that the XMD math operations are trying to meet the same levels of numerical precision as the C++ standard library math functions, which do kind of the same thing. So in theory, you'd imagine that they're about as fast as the STD log or STD EXP functions. The difference is that because these are operating on SIMD registers, we can apply the function to 4 values at a time rather than just 1 value at a time, like you would have with the usual standard library math functions. So that's kind of a neat thing. It's possible that I've heard that maybe in C++26, there's going to be some kind of SIMD support in the C++ standard library. So then maybe we could just use that instead. That would be cool. But I don't really feel like waiting until C++26 is available. So this is what we've got for now. But yeah, I've got some approximation functions that are a good bit faster than the XMD ones. Of course, the trade-off is that you lose some numerical precision, since my approximations are not trying to be as accurate as the standard library ones. So yeah, you get kind of a trade-off there as well. But again, it just depends on for a specific use case, is that trade-off okay or not? In this case, I think it is, but I'll give that a try in a second here and find out for sure. Yeah, I'm not loving it. It's still a bit too extreme at the end. Maybe I'm thinking about this wrong. Maybe I don't want maybe I don't want a higher number. Maybe I want a smaller number. Maybe I want something like, I don't know, 2.5 or something. 2.5. Rivolo says, yeah, I've been rolling my own PEDA approximations for tan H and then just clamp after a certain input. Yeah, that's pretty good. Part of the trick is to figuring out the right place to clamp so that you minimize the total error. And that's kind of a tricky thing. And again, it just depends on the specific implementation of your PEDA approximation, like what order you're doing and all that kind of thing. Doing approximations for log and exp are a bit harder because they're exponential functions. The places where the error shows up can be a little bit different. So yeah, I don't think I've seen a PEDA approximation that I really like for those functions, aside from maybe you're constrained to a certain range of what X is going to be. But yeah, as far as SIMD, I wouldn't recommend like using SIMD instructions directly. I would recommend finding a library that you like that has some nice SIMD wrappers. Juice has some decent ones, but I like the XMD implementations just a little bit better. So that's why I'm using them here. Let's see. Yeah, it's still just a little bit too, I don't know what the word is. Still just a little bit too, yeah, it's a little bit too right skewed, I guess, right? So maybe let's think about a different function instead. What if we do something geometric, something like sine of x? So let's make this a much lower frequency sine wave. Maybe something like that, yeah. And then let's make it bigger. That's kind of interesting, right? Because we've got sort of this, we've got kind of this interesting shape here where it's going to fold back down on itself, right? Again, I want to make sure that the slope stays less than 1. So I can do something like that. Yeah, Desmos is really nice for doing like wave shaper stuff and so on. I actually made a little thing the other day. Let me pull it up here because it's kind of fun. Yeah, here we go. So I was trying to, a friend of mine, Chris, was asking me about parameter smoothing. And so I wanted to show him kind of how a one-pole filter can be used as a parameter smoother. So this is your one-pole filter kind of unrolled basically over time. And so we can compute however many points we want. Right now I'm doing like, I guess 50 is good. We can see what's our parameter start value going to be. I'll put this back at 0. And then we can see what's our parameter end value going to be. And then we can say, okay, how long, like how many samples do we want our smoothing to take? And so maybe 38 samples, that means the smoothing finishes right around there on sample 38. Or maybe you want it to smooth really quickly, so maybe it's just a couple samples. So you can do something like this. So yeah, Desmos is super powerful. It took me a little while to figure out some of these tricks, but it's really, really, it's really, really useful. Anyway, sorry for the distraction. This is kind of interesting. Maybe what if we shift it a little bit, right? So maybe that's too far, right? Or maybe let's put the subtraction in the numerator here. That's kind of neat. Yeah. So now we've got, well, it's still not that asymmetric because the center point here is going to be at 4.5. So if we kind of zoom into our range, well, it is still asymmetric in the sense that it clips differently at the negative end than it does at the positive end. So that's kind of neat, right? You know what, let's give this a try. Oh, Revelo, which is Desmos did Fourier transforms. That would be super neat. I'd definitely suggest checking out Matt Title. I'm not sure how you pronounce his name exactly, but he did a really, really cool talk at ADC. Must have been ADC 2021. And he gives a ton of little Desmos interludes where he'll kind of show you a graphical view of what of whatever concept he's talking about. And he did have some that were kind of Fourier-like. I'm not sure if they're exactly what you're looking for, but it's definitely worth a look. And either way, it was a really cool presentation. But yeah, that was sort of the most advanced usage of Desmos that I've seen. It was really amazing. I should go back and watch that presentation too. Actually, that was a really good one. But yeah, so let's just see what we get from this this little guy here. But yeah, I think it'll give us something kind of interesting because you see we're kind of saturating at the positive end here, similar to what we've got with the sigmoid function. But then on the bottom end, instead of clipping like the sigmoid function and the hard clipper do, we're continuing to go and saturating, still saturating, but much more slowly. Let's give that a try. That's interesting, yeah. Oh. Okay, yeah, so it gets a bit unwieldy when you go to very high levels. So let's yeah, let's clamp this maybe. So we want to know where we're gonna hit our peaks, right? So let's see, generally with sine, you want to clamp at plus and minus pi, right? So here we want to clamp at plus or minus, yeah, plus or minus 9 pi. I guess it doesn't matter too much, right? Because we can just put our clamp here, right? Not clamp, clip. Clip at minus 9 times, well, here, let's just make this a variable. 9 pi equals 9 times, choose math constants. Right, so this is minus 9 pi to plus 9 pi on the other end. Yeah, so that should help make it that should help make it not blow up or get super fizzy when we get to very high drive levels. Yeah, all right. Cool. Yeah. Any fun news going on in the plugin world these days? I hear there's some drama with waves, but I haven't been paying attention to it at all. So I'm maybe a bit out of the loop on that. All right, let's see what we got. Yeah, so we've definitely got some asymmetric clipping, right? Yeah, okay, we're still getting some griminess when we get up to really high levels here. Oh, you know why I did this kind of foolishly? I clipped after I divided by 9. So now we just want pi, right? Now we just want to flip to plus and minus pi. Yeah, that was silly of me. It might be time to break out the guitar here. Play around with this new pedal a little bit. Yeah, so that's still a little bit I don't know. Still a little bit wackier than I want it to be. Yeah, like right up to there, it's really solid, and then past that, it's where it gets where it gets difficult. So maybe I'll need to spend a little more time on this and think about exactly how I want it to work. But yeah, let's have some fun with it here. Let's see if I can get my audio going into the stream here. So let's see. So I want this to come from the microphone. Cool. And then I'll have a black hole output. I want both of these to go to black hole. Maybe not quite so much of the guitar. And then, yes, I'm going to switch over Zoom to use the black hole input. And definitely let me know if you can still hear me. Testing. Hopefully. All right. Testing. Hopefully that's making sound. All right, we're going to try a little guitar input here. Okay, cool. Yeah, just making my voice a bit louder because this microphone doesn't pick up super well. So thanks. All right, I'm gonna mute my voice real quick so I can play. Nice. Yeah. So there's definitely a bit of a difference between those two clipping modes. Let's see how presence changes things. Yeah, so it gets a little freaky there at the high end, but yeah, that's pretty close. Maybe I'll leave out the asymmetric one for now, or maybe I'll actually let me try one thing real quick. Here, I'm gonna switch zoom back to the webcam mic. Okay. Yeah, let me try something just a little bit simpler here. Okay, George is asking, what are you SIMDing over channels? No, so I'm SIMDing over the different ports of the R-type adapter. So this R-type adapter has, I think, 10 ports. So I'm just doing a 4 at a time over those 10 ports. Yeah, so here, let me try this, where if I just do this function here, and then I skew it a little differently. So maybe we'll call this O for offset. Right. So what if we just put this offset somewhere else, right? So maybe over there, maybe 2.5 instead of 4.5. Let's give that a try. So let's see. Let's factor out the sigmoid stuff. Then we'll have our float for the offset here. And so this will be minus offset. And then here, this is going to be voltage minus offset over there. And so here, we're just going to call sigmoid with voltage and 4.5. Voltage equals that. And so we want to return this. And so here we want to do it just with a different number. So let's try 2.5, or maybe just 2. So this should give us a little bit of a different kind of asymmetric clip. So yeah, this should be an interesting change. man, I told myself I wouldn't go as long this time, but here we are. Oh, I guess you guys won't be able to hear this unless I switch back to black hole. Oh, interesting. Okay, so this one doesn't make any sound at all until you get up to somewhere around there. Otherwise, it's just like really, really quiet. Maybe let's try going asymmetrically in the other direction. So we'll, instead of 4.5, we'll do like 5.5 or something. I don't know, at this point, we're kind of just experimenting a little, but hopefully it's not too boring. But yeah, basically kind of what I wanted to demonstrate with going through this was just sort of kind of my process, or one of the ways that I go about doing some circuit modeling, both with like analyzing the original circuit and trying to make sense of it, doing some of the pre-computation that you might do with like pre-computation that you might do with something like Python or Mathematica, and then some of sort of the creative side where you're doing some trial and error and checking out different sounds and seeing what you like and don't like. So yeah, hopefully that's been fun for everyone and informative in some way. Maybe in order to combat it, we need to add some, just add some gain to it or something. I don't know. That's probably a bad idea as far as stability is concerned. Revelo's got a wave shaper that he likes. He likes y equals nh exponent x minus a, where a is a number in here somewhere. So, oh yeah, that's a good one. I've seen that kind of shape before. Yeah, that's a neat one. Maybe let's try that. Maybe that's what we need. So we'll boost it up here into the range that we want to look at. That's decent. It doesn't go quite down to 0. So maybe let's see if we can push it a little further. That's super close. Maybe that's too far. That looks pretty much spot on. Okay, yeah. I might run into a little trouble with how steep the slope is in the middle here. Yeah, I wonder if we, well, yeah, then we're gonna have to recalculate some of the other stuff there. So let's do a equals 0.2 or whatever. It's a VA. Right, and then we want to calculate the yeah, we want to calculate all of the offsets here based on A. So this is going to be exponent of x minus, well, yeah, exactly. Tan h of e to the e to the x plus 1 minus tan h of 1. Or replace 1 with a. Yeah, that seems right. A close to it. And then we just need this scaling, right? This is going to be, I mean, that's always going to be 1, right? So, well, no. What's going to be our ceiling here, right? Our ceiling here should always be 1, right? So we should always be able to just kind of do that. Oh, but we want to know what's the ceiling on the other side, right? So the ceiling on the other side is going to be what he was saying, or what Revelo was saying, which is tan h of a. So we want this to be 1 over tan h of a. Is that right? Not quite, no, because we still want it to cap out at 0, right? Oh, okay, I think I know what we got to do here. So we got to be plus tan h of a, and that puts the floor at 0. Yep, he's got it. And then we want to multiply all of that, because this will be 1 plus tan h of a. So we'll do all this divided by, oh man, divided by tan h of a plus 1, right? No. We're close here. So that's tan h of a plus 1. And I want it to go to 9, right? So, oh, okay. I basically had it. So that puts it at 1, and then I want this to go to 9. There we go. Yeah, thanks for bearing with me. You got it, Revelo. That's some good stuff. All right, so 9 over that. I'll move that out there. Just to simplify it a little. Cool. Yeah, let's give that a try. See what it sounds like. Are you trying to clamp between 0 and 1? Yeah, basically, or in this case, 0 and 9. Yeah, I could have let it go lower as well, but figured I'd keep to the op amp limits. Anyway, now we can play around with this a little bit and see where some of the different slopes fit in. You can multiply the x by a constant to change the steepness. Okay, let's try that. Add a slider for B. Oh, I see. And then that also changes the offset. Oh, I don't want that to go negative, do we? That's pretty cool. Nice. Yeah, that's a neat one. So around there is kind of where we hit symmetry, right? Somewhere around 0.75. But we don't want symmetry, do we? I'll stick with 1 for now, just so we can see what we get there. I'll leave that there for now. Minus 3.7 is what I have there for now. All right, so then we've got K and O, I guess, for our things here. So we've got K is going to be 9 over tan h of a plus 1. So O is going to be tan h of a. And then K is going to be 9 over O plus 1, I think. Yeah, it seems right. And so then the voltage is going to be K times tan H. K times tan H of EXP. X minus 4.5F. Minus A and then plus O. Oh, and then we've got another equal sign there that we don't want. Did I get that right? Seems about right. Let's give it a try. Yeah, thanks for sharing this wave shaping function. It's kind of a cool one. I think I've seen it before somewhere, but hadn't thought to use it here, so this will be fun. Okay, nice. Yeah, that's pretty cool. Cool, yeah. So again, we just have a little bit of this problem where we're not really getting enough sound out until we hit maybe like the 70–80% range of the slider there. Any reason why you have the outputs go from 0 to 9 rather than -1 to 1? Just because that's kind of what the circuit is expecting. So in the circuit, the op amp is clipping between 0 and 9. Obviously, in the green equation here, we're kind of going a bit beyond that range, and that's okay too. But yeah, I figured for this one, maybe I'll try to keep it in that range as well. So yeah, maybe let's try something hacky here and just crank the input voltage and see if that fixes our problem with silence in these certain ranges. Also like how these letters spell A-OK. That's fun. All right. See what we got here. So it gets a bit grungy here. Oh, and then it still kind of craps out quieter than that. Actually, if anything, it's worse. Maybe we want to go the other way then. Maybe we want it quieter. That seems counterintuitive, but who knows? Let's see what happens. Okay, that's kind of interesting. So we're getting a bit of a softer shape. So maybe that's okay, so long as I make up for it on the other end here. So I divide by 10 at the input, and then I multiply by 10 at the output. Who knows? Might be it might be a good idea, or it might be a very bad idea. We'll find out in a second here. Yeah, so then if this works out, then I'm just gonna replace these with some approximation functions that should help make things just go a little bit faster on the CPU. Because I think right now, doing two of these kind of expensive operations, once per port in the WDF tree and once per sample, is kind of using up a lot of CPU. So let's try not to do that. Oh, nice. Okay. It sounds a little quieter, even though the waveform looks to be, yeah, the waveform looks to be in kind of the same range, but just sounds a bit quieter, which is kind of interesting. Yeah, maybe I'll just crank the output even more just to see what we get. I don't know. And yeah, let's replace these with our, now that I'm more or less happy with how this is sounding, let's replace these with some approximations just so that we can hear what it's going to sound like in the end. So for the tan H, I'll use this algebraic sigmoid function that I've used elsewhere. So that has a lot of the same characteristics as the tan H, just with a bit more, it's just much faster. And then here, actually, I don't think I have these yet. I might need to update these submodules for this to work. Yeah, all right. Let's do a submodule update here. That's going to make our next compile take a minute, but that's okay. Okay, so yeah, we need to rerun CMake. And now we should be able to use this approximation function here. Yeah, that should be probably fast enough. So yeah, now it's going to need to do a full rebuild, so this is going to take a minute. 1 minus a absolute value x minus 1 to the 4th. Very cheap tan H. Yeah, I mean, that's very similar to the one that I'm doing here. Just instead of to the 4th, I'm doing an r square root. Yeah, it's kind of a similar similar approach to getting the same result. All the integrals are really simple. It is, but sometimes the absolute value can make the integrals get a little bit wonky. Well, I don't know. It might work out nicely for that one. Yeah, I don't think it would be too bad. But yeah, I mean, doing ADAA isn't too bad. Once you're able to do the integrals, it's just a little bit of kind of wrangling delays and stuff like that. Yeah, we did an ADA talk a couple weeks back, so I don't know if I'll do that again anytime soon, but it is something I'd like to spend a bit more time on just in general, because I do like messing around with ADA. But yeah, I think next week, well, I don't know if I'm going to do one next week, but the week after, or whenever I do my next one, is going to be working more on the multi-tool plugin that I've been working on last little while. Might be a little bit more UI stuff, since I think that's mainly what needs to be done with that plugin at the moment. And then I don't know, I really enjoyed doing some experiments with the Jai programming language, so I'd love to get back to that. or maybe do something else that's a little bit more kind of exploratory or something where, you know, something a little more out of my comfort zone. Circuit modeling is very much kind of where I spend a lot of my time, so it feels very familiar to me. But I did like some of the other weeks where I had to delve into something that I'm a little less familiar with. But I don't know. We'll keep it flexible. But yeah, I've been on here a little too long now. It's already like 6 o'clock where I'm at here. That's yeah, I've got other things to do today. So maybe after this test I'll call it a day. But I don't know, it's hard when you're iterating on something like this. But I always want to just keep experimenting and trying new things. All right, we've almost got something there. Maybe, well, I'll just play some guitar while I wait then. Yeah, my computer's not happy with me trying to compile some code all this time. Let's see. The iterated integrals are all of the form AXDN, absolute value, something minus something. So they all have the same form. Oh, that's pretty neat. Yeah. Yeah, having a constant form like that is always a handy trick if you're able to get it. Sometimes it's hard to get it though. Yeah, that's a little fizzy for my taste, but maybe it's not too bad. Let's see. Okay, we're almost done compiling here. Yeah. Yeah, updating the submodule kind of makes the next compile quite lengthy. There we go. All right, I'll switch back to black hole here so you all can hear this too, hopefully. Oh, what happened? All right, there we go. Testing. Hopefully you all can hear me still. All right, let's hear if we're getting any sound out of this. Maybe it's clipped in some way here. Yeah. Okay, yeah, maybe multiplying by 200 was a bit too heavy there. Yeah, okay, maybe I'll have to come back to this another time. I think I'll leave that implementation in there. But for now, I'll go back to the sigmoid basic thing with a different offset. And see if I can figure that out another time. I think there's something strange about the WDF that's making the clipping sound weird, or making the clipping behave strangely later down the line. So maybe I just need to tune it a little bit better. Let's see. Yeah, let's just try 5, see what happens. You ever put a sine wave through the clipper in Desmos to get a feel of what it does? Yeah, I've done that before. Usually I just kind of plot it. Like this, where it's just like the static wave shape. But yeah, I've done some sine wave stuff before. It's not too crazy. Basically, what you might do is like like this, and then this would be like g of x there. right, and so, well, it's gonna look weird because I've got all these other ones showing, but yeah, that would be like your thing here, although maybe this is not a good example because it's so offset, right? So we've got like something like that. Yeah, maybe that's a bit heavy as well. I don't know, something like that. Anyway, here we go. Final test, and then I'm calling it a day here. Yeah, all right. So that's good enough for now. I'm just gonna finish up here just so I don't end up spending another 2 hours sitting here and fiddling with these wave shapers as much as I would love to do that. Yeah, I'm just gonna make that offset a little bit less aggressive. Yeah, all right, that'll be good. Cool. So yeah, that's gonna be everything for today. I'm just gonna uh commit all this stuff to the Git repository, but yeah, I'm happy with how this went. So yeah, this was fun. Hopefully you guys enjoyed it as much as I did. And yeah, I'll be back maybe next week, maybe the week after with another stream. So yeah, hopefully we'll have something fun to talk about then. And yeah, thanks everyone for tuning in. Thanks Revelo for the fun suggestions of wave shapers to try out. And yeah, I'll be back either next week or the week after.